A block sitting horizontal surface is pushed against a spring. The spring P that attached to the wall, compressing the distance x, as shown in Figure 1. The block is then released from rest. The block slides along the horizontal surface up a ramp. So after being released from the compressed spring, the object can slide up to the top here, position B, and it has the maximum height from its center to the ground here as h max p. The frictional force between the block and the surfaces are negligible. Okay. What is the question A? Where the question A? Let me find it. The student compared the hex max for the spring with the maximum hex Q achieved different spring Q. Each spring exerts a force of magnitude F on the block that varies as a function of the distance x. The spring is compressed, as shown in Figure 2. For the spring P, the force Fp is proportional to kx, therefore the graph of the string P is a straight line, where k is 100 Newton per meter. For the spring Q, is follow this law, the half the square root of x, and therefore it's a curve like this. Okay. For the experiment, the block is pushed against one of the spring. Compress the spring a distance 0.01 meter. The block is then released from rest. In trial 1, the spring P is U, and in trial 2, the spring Q is U. On the following dots represent the block of trial 1 and 2. Draw the label of the forces, not components, that exert on the block at the instant the block is released. Each the force must be represented by a distinct arrow starting on and pointing away from the dots. The length horizontal vector should represent the relative magnitude of horizontal forces, and the length of the vertical vector should be represent the relative magnitude of the vertical forces. Okay, there's no friction, right? Frictional forces between block and all surfaces are negligible. Yeah, negligible. So for each object in the two trials, they have three forces acting on them. Firstly, the weight. Secondly, the normal force, which is equal to the weight and opposite to the weight. And lastly, the elastic force of the spring. This is the Fp, elastic force of the spring P. Okay. Yes. Similarly, for the Q, the weight is the same, drawing with the same length, like 2 centimeters. Okay. This is a normal force, also equal and opposite to the weight. And this is the force of the spring, which is smaller, Fq, because you can see on the graph here, when the compression is 0.01, meaning at here, 0.01 meter compression, the force of P, this is P, this is Q, so force of Q is vector. Okay, sorry, so the force of Q is vector. We fix that. Fp is smaller, and Fq is vector. So you can draw Fq like Fp like this, and Fq vector. Or you can even use one tiny cell there to represent the magnitude. So Fp is 1 Newton and Fq is 2 Newton. Okay? Yes. Initially 2 Newton and Fp here is 1 Newton. So this vector Fq must be twice Fp. Double the length, So that's the first one. Yes. Question 2. What feature of the graph could be used to estimate the work done on the block by each of the spring at a spring is compressed? Work done equal to the area under the graph, because this is the graph of force visit distance. And we have the definition of the work. Oops. PQ. Okay. The work is equal to the force times the displacement. But this simple formula is only valid when the force is constant. For the varying, a changing force like this, we need to take the integral of this thing with the displacement dx. And this integral is the area under the graph of the force versus the displacement. Okay? Yes. Area here. Yeah. You've learned calculus, so that is the meaning, the significance of calculus. Yes. So the answer to this question is simply the area under the graph of f, which is a function, of the displacement x. The x here is not displacement, but the compressions of the spring, and also equal to the compression. It doesn't matter. Just try the graph of f. Visit there. Stop there. Question 2. There is one compression distance x0 for which the maximum height reached by the block is the same regardless of which spring, meaning the area must be the same. The spring P and Q is U. Predict whether the value x0 is greater than, less than, equal to 0.04. Use the graph to justify your answer. The maximum height is the same, meaning the work done by the spring is the same, meaning the areas under the two graphs must be the same. So we need to use the graph somehow to determine x0, initial compression. There's a graph. x0 initial is compression, right? Compression x0 for which the maximum height reached per block is the same. Compression, okay. The horizontal values on this graph is the compressions, meaning at different compressions of the springs P and the spring Q, we have different amount of work done by the expansion, by the elastic force of the springs. And therefore, the compression value that the two areas are the same. We need to determine the position where the area is the same. I think it is here. So that the area of this triangle is almost the same with the area of this curve, right?
Yes.
You see the area of the triangle, and for the curve, I would choose another color, the orange color. I think it's equal to the area here under the curve. Yeah.
Yes.
Or if it's not here, it could be here. No, a little bit greater, I think, because we have some extra area here. So we need some extra area up here to make up to that loss increase of the area, huh? Yeah. So it must be greater than 0.6. Greater than 0.06. 0.06. So it's not smaller than 0.04 as mentioned in the questions. Here. Less than, equal to, greater than. Okay, so our answer is greater than. Okay.
Yes.
Reduce that thickness also right. Okay, according to the graph, you can write that or not because they already mentioned it here. So just no need to say that. Just say that for the two areas under the two graphs to be the same. Zoom in to make it easier to write. To be the same. So that the object reaches the same maximum height. The sentence inside the bracket here, you can not writing it, huh?
Yes.
Just eliminate it. The same. The area is the same. The initial compression must be greater than 0.04. Initial compression have to be greater than 0.04 meter. Approximately 0.065 meter. Again, extra information. So the first one seems not very difficult, huh? Easier than the multiple choice question there. The axis provided, both string P and Q. Probably the question in this book is too far difficult than the real test. So I will try my best to find a past paper, field past paper. These three response question is definitely the real past paper, but it's just hard to find the multiple choice question. On the axis provided, for both spring P and Q, sketch a graph. The maximum height reached by the block as a function distance. Each spring is compressed for the value of x ranging from 0 to 0.1. Clearly label the curve for spring P and Q. Maximum height reached by the block. Up here we have the graph of the force versus the distance, and the area is the work, and that work will be equal to the potential energy, the maximum potential energy that the object gains when reaching the maximum height. Okay. The work done by the elastic force, meaning the area, is equal to the max potential energy. Okay.
Yes.
And the work here is calculated by the area. It is the integral of the force. It depends on both cases. So for P first, For P, the force is linear and represented by k times x dx. So this integral is 1/2 k. We know the value of k, which is constant 100 Newton per meter, times x squared, right?
Yes.
And taking the integral from 0 to x there. So this is the work, and it's equal to the potential energy mg h max. Therefore, h max is proportional to the square of x, is 1/2 k over x squared over mg. Basically, it's proportional to x squared. Proportional to x squared. So this is a parabola. This is a quadratic function, right? X squared here. So for the spring P is a parabola. Okay.
Yes.
Quadratic. It will be harder for the spring Q. Let me write down here for the spring Q. But I like this one. Yeah, it's been a long time that I teach APC. Most of my students, they study IB or A level. So similarly, for the spring Q, we have that work is the integral from 0 to x of another function, which is c times the square root of x, x power 1/2 dx. And the integral rule, right? You already learned. You got a beautiful and excellent mark 5 of the calculus,
Yes.
So here is c to the power of x plus 1, which is 3 over 2 over 3 over 2. So that's 2 over 3, And it's equal to, again, potential energy maximum. Okay.
Yes.
So h max here is m2c over 3 mg x power 3 over 2. So this is a polynomial function, and you need to use a graphing calculator to find the form of this function. I don't remember exactly how it looks like. Probably the power 3 over 2 is less than 2, less than 2, and therefore it is lower, right? We can check with a graphing calculator. The function is like x equal a constant k, assuming k is like 2, okay? Or just ignore that. X to the power 3 over 2. There, you see? Compared to a quadratic x squared. Oops, here's a y. See? So this is our graph. It is under, meaning, sorry, the red one, power 3 over 2, is above the quadratic, but the coefficients are different. The coefficient here is 2c over 3 mg. The coefficient here is 1/2 k over m. So we need to do some calculation, or you can use a graphing calculator to find the intersection point of the two graphs, knowing their coefficients. Okay.
Yes.
Here, let me complete the coefficient. calculate that. The value of C is 20, right? Find that value again. Yeah, 20. Okay. Do you have a graphing calculator? I think you do.
Yes, I am.
Okay. So C 20. So 2 times 20 is 40 over 3 times of M. M cancel out, huh? Wait. No, not canceling out. Do we know M, the mass of the object? We know K, but there is no information about the mass. Doesn't matter because the mass is the same for the two formulas, and therefore we can compare them without knowing the mass, huh? Yeah, even G. Okay, so that is 40 over 3 mg. Mg here, and this is K is 100, and this is 50 over mg, x squared. Okay, x power 3 over 2. So now we need to compare the two coefficients here and here to find their intersection point, and which graph is above the other graph, huh? 50 compared to 40 over 3, meaning this coefficient is smaller. So let me make that here, 50 here, huh? And this is 40 over 3 there. So zooming in, the graph of the spring Q is above the graph of the spring P. Okay, and this is the intersection point. You can find that intersection point using the graphing calculator. But the question here, I don't think that we need to clearly label. Sketch the graph. Okay, sketch. Don't need to be very accurate. Okay, just the approximation curve. So for the spring Q, that is a red curve here, and for the spring this is for the spring P, and now for the spring Q, it is above, huh? Oops, not that straight. Meaning it has a intersection point, but basically a curve also. Okay. And the point where they intercept each other is when the work is the same, which we determine to be greater than 0.06, approximately 0.065, huh? Remember the question above?
Yes.
Yeah, so here. So that's the point of doing that question first. 0.065 here, the intercept here, meaning the work is the same. Scoring guideline. Here. Beautiful. 0.07, huh? 0.07, not 0.065. Fix that one. Here, my estimation is 0.065, but it's not very accurate. We should change it to 0.067, huh?
Yes.
0.07. Change the color as well. And therefore the graph below here is 0.07. Erase that and do it again. Oops, only the green one. The red one was beautifully correct. 0.07 here. The point the intercept is here. Draw it a little bit curving through that point and going up continually there. Okay, that's it. So paper 1, the spring Q is attached to the wall and it is at equilibrium as shown in figure 3. The block A has a mass of 0.12 kilogram and the block B has a mass of 0.07 kilograms. The block A is held at rest at the top of the ram and the block B at rest on the horizontal surface. Now there are two different blocks, huh? One on the ram and one the other at the bottom on the surface in front of the spring. They will collide when the block A is released. And the change in the vertical height of the block A is 0.75 meters. After the collision, the blocks stick together and move to the right, compressing the spring. Frictional forces between the blocks and all surfaces are negligible. Calculate the velocity of the two block system immediately after the collision between block A and B. So for this question, we just need to use the conservation of momentum. Okay. Remember that in the two types of collision, including both elastic and inelastic collision, the momentum is conserved as long as the frictional force of the external environment, external forces are 0. So, but we need to find the velocity of A right before colliding with B. VA right before the collision, the collision. And to find that thing, this thing, we need to use the conservation of energy. 1/2, mg times h, the height of the block A, will convert this potential energy totally 100% into the kinetic energy 1/2 m VA squared. This is the mass of A, MA. We can simplify m and m on both sides. So VA is 2 times of GH over, that's it, 2 times GH square root, GH, there, before the collision. And then the conservation of momentum conservation. The mass of the block A times this velocity right before the collision. We can calculate that value. Square root of 2, which is 9.8, and the height is 0.75. If you want to take more accurately, A1, and take 3 significant figures. The last result, the final result, we only need the 2 significant figures because the height 0.75 is too significant. Square root of 2 times 9.81 times 0.75. The velocity is 3.84. 3.84 rounded, meter per second. So replace here, MA, the mass A, write that formula first, plus MB, VB here is 0 before the collision, okay?
Yes.
Equal to, they stick together, the mass added together, MA plus MB, and their final velocity that we need to find. MA is what the mass A, 0.12 kilogram, 0.120. The speed is 3.84. Added with this thing is 0, equal to the sum of the masses 1.02, and the mass of B is 0.070, and speed here is what we need to find, and calculate that easy. So please do the last calculation here. V, what is its value?
20.8.
That's fast. It doesn't make sense because the speed of A before the collision is only 3.84. It should be smaller than 3.84 because the mass now combined. Take this value on the left and divide the total mass. Okay. The answer is 2.4. Okay.
Yes.
It must be smaller than 3.8 meter per second because now the mass greater, they combine. Calculate the maximum compression of the spring, also easy. Conservation of energy, meaning the total kinetic energy of the two blocks, 1/2 MA plus MB times the speed that we have just calculated here, 2.4 square with kinetic energy, convert totally into the potential energy of the compression of the spring, which is 1/2 kx square. X here is the maximum compression. Okay. So just use the formula and we can find the maximum compression. 1/2 the mass 0.12 and the other mass 0.07 The speed is 2.4 square, 1/2 the spring constant, we know it. The spring Q, what is spring constant? Wait, the spring Q has a variable changing spring constant. It's not a constant spring constant. Oh, that makes it difficult because you see here the gravity a curve, huh? So instead of using this formula for 1/2 kx squared, we need to change it to an integral for Q, because a changing spring constant of Q, which is the integral from 0 to the maximum compression of Q. Here is the C times the square root, meaning x power 1/2 of dx of Q. This is the potential energy of the Q, of the spring Q when it is compressed. Okay. And this integral result in C. C is 20. Okay. Newton per meter. This result in 2c x power x max power 3/2, because the lower limit here is 0. Okay, over 3. C 20. Just replace that value, and then finally you can calculate x max. Okay, please do the last calculation. I like being challenged like this. Okay, have you found the maximum compression?
0.8.
And the answer here, 0.12. Yeah, basically the same solution, you see here.
Yes.
This formula exactly the same thing with my solution, but what is the mass m here? Yeah, 0.19, meaning the sum of the two masses of the two blocks. Yeah, basically the same. So be careful with the final calculation. Okay, let's calculate x to the power 3/2 first, huh?
Yes.
X to the power 3/2, and then we will take the other power later. Taking all the value on the left side here times 3, and then divide 40. Open the calculator. All the value on the left is 1/2 of 0.19. 1/2 of 0.19, and times the square of the speed, which is 2.4 square. And then this is the thing on the left side times 3. And then divide 2 times c, which is 40. Okay, this is the x power 3/2, 0.04, 0.041, 0.041. Check that again. Yeah, and so x is this value to the power of 0.041 to the power of 2/3. Okay.
Yes.
This value power 2/3. Here, 0.1119. Very close, 0.119, which is rounded to 0.12 of the answer. Okay,